today also we will be talking about the vector autoregression model. However, will we see there is a certain problem with that? Then how we will be able to improve that model? Then we will be also talking about a related concept of the multivariate time series, that is the Granger causality. So in the last class what we have talked about, where we have two forms. One is the in primitive model. So here if let's assume k is equal to 1, that is if the lag is equal to 1, then we can represent these two equations which represents the vector autoregression of two variable for lag 1. And this above equation can be expressed in the matrix format as like this, where if I are taking the contemporaneous term, the left side, then we can represent this in the reduced form AYT B0 B1, where the definition of these matrices are given here. And a reduced form where can be represented like this, where this yt is equal to a0 a1 t minus 1 where et, where the definition of the various matrices are given here. However, we have certain problem here. So this is the basically standard form of where, or what we call the reduced form of where. Now there are the certain issues or problems we do face in the vector autoregression. So first what we face in primitive vector autoregression model, we face the estimation challenge due to the simultaneity bias. Then the solution one is, if we assume there is no contemporaneous relationship, that is the absence of contemporaneous relationship, then we can solve that issue and we can estimate the vector autoregression. However, that is very restrictive approach. Then if we assume there is the presence of contemporaneous relationship between the two variables, then the solution was to change that to the reduced form of where. However, after transforming it into the reduced form where, it is quite impossible disentangle the effect of the shock of one variable on the other variables. Then the solution for that was basically a Cholesky decomposition. So what is the Cholesky decomposition? Basically we decompose the variance covariance matrix into the triangular form, where we then once we do that, so during this process what basically we do, we assume that, for example here in case of the two variable, that is at least one variable does not have contemporaneous effect. So then we make a diagonal triangular matrix where we assume there is no contemporaneous relation from one variable to others. However, we can assume other variable may have the contemporaneous correlation. However, in that case, we have the two issues. One, here we are assuming one does not have a contemporaneous effect on the other in case of the two variable case. So sometimes it may be represented the theory, but here most of the time we arbitrarily assume that. Second issue with this kind of restriction is that the ordering of variable does matter. How does matter? For example, let us say we have three variables xt, zt and yt, and if you are using the Cholesky decomposition in this same order, then what it means? It means that xt do have effect on zt and yt, and zt do have effect on yt. However, zt do not have effect on xt. Similarly, yt also do not have effect on xt, and this zt do not have effect on yt. So that means ordering of variable does matter while we are using the Cholesky decomposition. So the first thing in this case, arbitrarily we assume in one of the variable does not have contemporaneous correlation on the other. Second, this ordering of variable matters. Third, here the restrictions come from the arbitrariness. So in that case, what we will have that issue that we will not be able to disentangle the shock of other variables on the one variable on the other variables. So an alternative for this issue is the structural vector autoregression. So basically, what is the structural vector autoregression we do? What we mean by the structure in the term of structural vector auto. What is the term structure mean in the structural vector autoregression model? So let us say what we have. We have a reduced form where of standard where yt is equal to a0 a1t. So here basically we are concerned with the variance and covariance matrix of this. Here the variance and covariance matrix contains the variances of endogenous variables on its diagonal elements, this, and the covariances contains on the off diagonal elements. These covariances basically have the information about the contemporaneous correlations between xt and zt here in our two variable case. And here the covariance matrix of this standard where if you look here, these are the symmetric. So if it is in the symmetric in nature, that means the elements of the top right diagonal is equivalent to the lower triangular matrix. This basically reflects the idea of correlation between two variables, but does not reflect the idea of causality here. It do not reflect the causal relationship, it only reflects the correlation when you are assuming the symmetry. So then how we can measure this, how we can disentangle the causal relationship into the structure of vector autoregression. Basically this causal relationship, what we basically mean by the structure. Or we can say we can directly measure the impact of one variable in the on the other variable using the structural vector auto formation. So what is the structural vector models basically we wanted to do? Basically we wanted to have to examine the causal relations between the variables and to add the structural restrictions onto the vector autoregression model, primarily derived from the theory, not from arbitrary. Third, here we wanted to examine the impact of individual shocks on the other variables. So that's why we turn out to the structural vector autoregression. So let us first see what is the mathematical specification we have in structural vector autoregressions. Let us say if we have order P, then we can write ayt a0. So here this A is the vector of endogenous variables, that is the contemporaneous correlations. This yt is the basically vector of endogenous variables. This A basically reflects n by n matrices capturing the contemporaneous relationship, and here this AI is basically matrices capturing the lagged effect of n variables, and this ET is the vector of structural shocks. Here each shock in ET, this error term, is basically independent and captures exogenous factors, unlike the purely autoregressive disturbances into the vector autoregression model. So in this case we have this structure. Let us see how we can have the reduced form of the structural vector autoregression. So that can be written here A2 is equal to A0, where basically this A0 star is nothing A inverse of A0, and this AI star is nothing A inverse into AI, and this UT is basically A inverse into ET. So this is the basically reduced form of the structural vector autoregression. Here if we see this reduced error term are the function of structural shocks, allowing the system to be estimated as a standard where. So that means like the primitive where we have formed the reduced form of where. Similarly here structural vector autoregression we can change it to the reduced form of where and we can estimate this particular model. Then how we can identify the structural parameters? So before that, what are the challenges we have? The similar challenges here we are facing as we have faced into the primitive way. So basically this structural coefficient in A and ET cannot be estimated directly from this reduced form where. Basically why we will not be able to estimate? Because it will be under unidentified. So what is the solution we have? Imposing the theoretical restriction such as it should be the solution of this problem is imposing the theoretical restriction. There we have imposed theoretical restriction based on the Cholesky decomposition. However, here we are putting restriction derived from the theory. However, at least there should be n square minus n upon 2 restrictions on the matrix A that we have to put to estimate this reduced form of structural vector autoregression. What are the implications or what is the importance we have here? Basically, this restriction should be rooted in the economic theory to be meaningful. However, this is also the weakness of the structural vector autoregression where it is being claimed that it becomes very subjective decision of the researchers. However, most often this subjective decision of the researchers is derived from the theory. So therefore it is believed that structural vector autoregression is better than the normal form of the vector autoregression. Now how we can identify those restrictions? There are basically 4 approaches to model this structural relationship between the endogenous variables of a structural vector autoregression model. So one, what we known as the A model, second what is known as the B model, and third is known as the AB model, and fourth is basically what we know as the long restrictions by the Blanchard-Quah, and it is often known as the Blanchard-Quah restriction. So let us see one by one what we mean by here. So basically this A is in A model what it assumes that the covariance matrix is diagonal. So once we assume that diagonal, that means it only contains the variances of the error term, not the covariances. Then this continuous correlationship between the observable variables are described by an additional matrix A, and then we multiply that matrix with the reduced form of where. So now we form an additional matrix where we put the restrictions derived from theory, then we multiply this with the existing reduced vector form of structural vector autoregression. Therefore, it is known as the A model, where this AJ is basically, AJ star is basically nothing, A into AJ. That is the multiplication of this matrix A with this A1, A2 up to AP. So here we are representing this A is AJ star with this A into AJ. Then here Vt, that is this new T, that is basically nothing but A multiplied by this error term, which follows this particular distribution here. So let us see here what we mean by that. For example, let us say, so this is the A matrix, and here we put the restrictions based on the subjective theory or the restrictions derived from the theory. We change the elements of this A matrix. So here the matrix A contains at least k into k minus 1 upon 2 restrictions to be able to estimate the reduced form of structural vector autoregression. Then this upper triangular elements of the matrix are set to 0, and the elements below diagonal are freely estimated where we put the restrictions here. So it would be possible to set more than k into k minus 1 upon 2 restrictions. However, in that case this model is basically said to be over-identified. Then what is the B model? So in this B model basically describes the structural relationship of the errors directly by the adding a matrix B to the error term and normalizes the error term variances to unity, so that here instead of multiplying with A matrix, here we are multiplying this epsilon T, that is the error matrix, with the B, and we formulate B matrix in such a way that this epsilon t matrix becomes an identity matrix. So here ut is b into epsilon t. So here epsilon t basically an diagonal matrix. Then the another approach is the AB model, which is basically mixture of the both A and B models, where the errors of the variance are modeled as AUT into B epsilon t, where epsilon t, that is the error matrix, is nothing but a diagonal matrix. Here we require to specify more restrictions than when we use only A or the B matrix. Then the last approach is the long run restrictions, what we call the Blanchard-Quah restrictions. So long run restrictions, basically if you see theory, for example, we know that money neutrality. So what the theory of money neutrality says? It says that in the short run, monetary policy or the money supply may have impact on the GDP. However, in the long run, it does not have any effect on the GDP. Suppose we wanted to model such restriction or we wanted to put such restriction on the vector autoregression model. So then we use this Blanchard-Quah approach. So basically what it says that it does not require to directly impose any restriction on the structural matrices A or B. Rather, these structural innovations can be identified by looking at the accumulated effects of the shocks and placing zero restriction on those accumulated relationships, which basically die out and becomes zero in the long run. So we do not form the structural matrices, rather than we find out the accumulated effect, and there we basically place a zero restriction on that. To understand better, let us see an application of this structural vector autoregression. So here let us say we have the system variable, that is the 6 endogenous variables we have, and those are, let us say, oil prices, industrial production and inflation, real effective exchange rate, call money rate, and the monetary aggregates. Here the shocks or innovations of this is represented by this particular terms here. Now what basically we wanted to do here is that what is the real macroeconomic responses, that is we are concerned about the responses of output and inflation to a oil price shocks. So for that what we construct this particular matrices. So this is the short run restrictions for the identification we put here. So if you see here the diagonal, this above the diagonal matrix is basically all are 0, and it is basically lower triangular matrix. So in this case basically what we are wanted to see, for example oil price or output, that is each variable is assumed to be impacted contemporaneously only by specific other variables. Not all variables are contemporaneously affect to each other. For example, here E out, that is the output, depends on the oil prices but not directly on the exchange rate. So if we see the structure here of this restriction, this clearly shows us that we are assuming that this output depends on the oil prices but not directly on the exchange rate. So if you see here this particular structure here, it confirms this particular situation here, that output does get affected by the oil prices but not by the exchange rate. So accordingly we can put the restrictions of 0 and others. So these has to be estimated from the data, and these are, we have assumed these effects are 0. So that's how we put the restriction derived from the theory. Then the second aspect of vector autoregression is the Granger causality. So what is the Granger causality? So the Granger causality basically it says that whether a time series, let us say here yt, can predict the another time series, let us say zt. So that's basically here we are looking in the Granger causality. So whether the series of yt can be predicted using the series zt or not. So basically what we wanted to test here, we will say that yt Granger causes zt if the past values of yt improve the forecast of zt. So if you are not able to improve, then we will say there is no Granger causality. Mathematically, what we can say that if the yt does not Granger cause zt, if all the coefficient of lagged yt terms in that is A21 or that is A211, A222, A22P is equal to 0. So basically what we say here that this zt, if let us say is the function of what we have in the second equation, that A21 yt minus 1 plus A22 yt minus 2 plus up to y A2p and yt minus p. If all the coefficients here is equal to 0, then we will say that this yt does not Granger cause zt. And we use the F test for this test. So here the null hypothesis that if all lagged yt terms in predicted zt are 0, so it can be generalized to the n variable system by testing the lag terms aig for all the terms we can see here. Then there is another very related term is the exogeneity. What is the difference between Granger causality and exogeneity? Here the key distinction is that in the Granger causality considers if the past yt helps predict future zt, where the exogeneity implies that zt remains unaffected by the current values of yt. So the exogeneity basically refers the contemporaneous relations where we do assume that yt, current value of yt does not have impact on the zt. That's what we mean by the exogeneity. Extension of this exogeneity is this can be given an example on the variance moving average model like this, where yt does not improve forecasting of zt despite phi 21 is equal to 0. So if this becomes 0, then we can indicating that while yt does not Granger cause zt, zt is not exogenous. Then there is the extension of this exogeneity, where basically what we call the block exogeneity. What is the block exogeneity basically? Here basically evaluates if an additional variable W2 in addition to ZT impacts other variables in the system YT and ZT. That is basically known as the block exogeneity. So here the test statistic likelihood ratio test for the exclusion of WT, that is for the third variable we will do. So the statistics, this test statistic we calculate using this particular formula, where it follows a chi-square distribution with the 2 degrees of freedom. So that is the what we mean by the block exogeneity test, where we evaluate that if an additional variable WT impacts other variables in the system, for example YT and ZT. So then we say the block exogeneity test. To better understand the concept of Granger causality, let's consider an example of the vector autoregression of order 3. So here we are assuming that the two variables are, one is the y12, another is the yt2. So here y1t, the first variable, depends on its own lag here and on the lag of other variables. So that's what we have here. So this is the 3 lag variables we have. Similarly, yt2 depends on this. In this case, how we test for the Granger causality? So it will be difficult to which sets of variables have significant effects on each dependent variable and which do not. And in such cases, often we use the Granger causality. So here what is the basically we have? Let us say if lags of y12 does not explain the current yt2, implied that restrictions, if you look here for this equation, so y12, it is not being explained by the current variable of y22t. So in that case what we assume, the beta 2 1 is equal to 0 and alpha to 1 is equal to 0 and gamma to 1 is equal to 0. So all the terms like terms of y1t is basically we are assuming equal to 0. So here what we are assuming that all the terms of y2t, that is beta 1 to here like 1 and thus beta, then another here we are assuming this term is equal to 0 and here we are assuming this term is equal to 0. So all these three coefficients of y2 we are assuming 0, and it implies if it is all 0, that means this y2t does not lags of y2t does not explain the y1t. Similarly, if we assume that the lags of y1t do not explain the current y1t, so then what we assume here, this y1t is not being explained by its own lag, so that means this beta 11 and this alpha 11 and this gamma 11 should be equal to 0. So that's what we have, and similarly we can do for the y2t. So to test this we will go for the hypothesis testing. So here basically F test can be used for this analysis, and that is basically nothing, the Granger causality. So basically here the Granger causality test seeks to answer following questions, that is, do changes in y causes changes in y2? If y1 causes y2, then lags of y1 should be significant in the equation of yt. Similarly, if this is the case, we say that y1 Granger causes y2. And on the other hand, if y22 causes y1, lags of y2 should be significant in the equation for y1. And in this, if this is the case, we say that y2 Granger causes y1. If both sets of lags are significant, then we call there is the bidirection causality. So today we have discussed the structural vector autoregression and the Granger causality. In this we have discussed why we go for the structural vector autoregression from the normal vector autoregression, and what we mean by the Granger causality and how we test for that. In the next class, we will talking about the quantigration and the vector error correction model. Thank you so much. See you in the next class.